1 hour in the morning, 1 hour in
she starts giving away
and if
money,
you work
gold,
that,
bullion,
those times,
art,
and you work the
so that she has no
pages,
money, so
you're
that
fine.
if she loses, they have
There's
nothing
also
to grant,
like-
and her friends
so like,
have, she register her presence, pay the taxes and get rid of all the property, but eventually she wins. But then the software and the,
I mean, they're working on, I
algorithm,
think the construction was for
they
this.
incorporate in the fact
For
that
the
it's
construction
used for evil. You know, like to keep the madness, and then you have the subprime wealth and all that. So she was like many years before the subprime trying to free the people.
The thing is, it does not
And then
fix
she,
the income
well,
situation.
when she finishes
But
all
actually,
that,
like a lot more people
she
should
doesn't want to be financial
the
advisor
benefit in
anymore, and
itself.
she doesn't want to like so she's fed up. So she starts a newsletter, and the newsletter grows. So today she has a website with a paywall, $25 a month. Is solari.com, and she records like her podcast videos. So she analyzes the market, everything, etc. And she has a company with financial advisors who does her philosophy. And her philosophy, she has a big plan which is called Come Clean, which says don't invest in evil companies. And then she has a whole methodology of how to tell if the company is evil or not, and how to tell that the investment is actual good investment for the community and all that. She has a lollipop index, which says if a child goes buys a lollipop and comes back home, how much do you trust that she can go along in that community? And that's the lollipop index. So do you want to live in a, and she saes that how much like the sheriffs in America have a lot of power yet, and they are still have a lot of community participation in the sheriff. As like COVID or lockdowns came, the sheriff could just say, oh, whatever, just do whatever you want, don't wear muzzles, and you're fine. And so she has all these ideas, and
Yeah, so that's what
so there are two
I was
books on
thinking,
her
like,
reading list. So I'm back
like
in
there's so many
the
things, there's
rabbit
confused.
hole now.
There are so
This is
many
the first, because there's a lot of tech involved, but then I'm gonna go through two books on how private equity, because what they do is they destroy the economy, they destroy pharma, they destroy everything.
And that reduces the amount of time on the road. It's really not for everyone.
Yeah.
Even like if you go to the license, like if you combine a license system with a bus system, then those things combine.
In the UK we have NHS, public health. Historically, out of 10 men who have a heart attack, one will never go to the hospital. So it has always been common.
You said you've been in Florida. Which part?
And then he's all distracted, and you have pressure.
Yeah, I've never been to
What's happening to you? I have a heart attack.
Yeah.
When did you have this heart attack? 10 days ago. 10 days? And you are now here? Yeah, because I'm not feeling well. I was at home, I was waiting, but now I
Not
really
so
need
much
your
this
help.
time.
Because they
I have
don't
like
trust.
4.5
I think we're probably gonna have to talk about that in the
to
future.
drive to the side of the state.
My goal here is to try to get
for the
I'm one of
launches,
them.
but
I would never go to the
Okay,
hospital. Even in the
this
hospital.
was
also you don't
something
know
that
if it is going to get
I
paid.
had a little bit of knowledge about before I kind of started studying this stuff and all the different event formal methods and stuff that I was attending over the last several years. I had a little bit of knowledge about this,
I have too
but
much selenium, we eat some
just
Brazil nuts.
very,
Now I have
from
too,
a very
too
long
much
way.
selenium. Now I have too much
I
selenium.
didn't
Stop the
really
Brazil
come
nuts.
from the type
And
theory world. I came
4
from
times a year you can make your diet. And then there's
like
there's
this.
all types of information.
Yeah.
So I want to have like 4 board exams a year.
In a sense, my math background was not in constructive
And I
engineering.
don't trust, so.
But I was mostly in the CF side of the world, but also,
So maybe.
my introduction to formulas
majors
came more from like we just preconditioned continuous mathematics. And so from kind of opposite directions. So the intersection is interesting, how weird that it existed, but it didn't have a deep
So that's just the base
So
camp.
get in the facility.
So in a sense,
Yeah.
I knew about the union, even though I was missing
But then,
years.
they have like, in a restaurant, some restaurants have like the glass.
We'll get
and
started
people
here in a
working behind the
second.
glass. If you have that glass, the person who took the blood goes behind.
Just canceling it.
As you can see with
The weather was too
They
dangerous.
do everything analog. They write in a piece of paper. In the end, you get that piece of paper that you put in the app that is like a secure app, privacy app with your privacy.
Privacy aspect,
And then they give you also the byproduct. So all the rest of the blood, everything, your feces, whatever you get back, so that they don't do the DNA and not doing put you in the database. Because the databases are hacked like this.
Sure.
You-
So,
Yeah, like the 14 years old, so, and especially in health that has like this very little IT investment. So these databases are really out there. So when they have TV, they have everything, you don't want a clone of me like walking around, like, you know. So I think this would be the hit, you know, you could have this app all over the world, and it's so simple, it's just go back to analog, you have your blood.
So the question is, how do you validate that there's a market? Really like India to be interested in
It's like,
that.
once they're strong enough.
Also, like, the other second people.
I feel like those are companies. So yeah.
That's
As a
I'm creating monetary industry, so you need to find a lot of marketing people on the private
It's
side.
testing before market.
Yeah. Yeah, it needs to be economically viable, and economically viable, and we need like some doctors or people in the sphere of laboratory, because there's like a lot of compliance, there's like a lot of regulation. So you have to follow everything as all legal listed.
Start of this month, I have to be here. I don't do like different drugs, because the window is down, so I could actually.
No,
go
but
to
that
drugs.
thing with
Can't do that
education,
anymore
you can do
because
like,
I
if you have to burn it,
I don't
you
live
can
in
burn
downtown.
it yourself.
I don't live in downtown at all, so.
Or you can even have the burner, or you can have the burner there, you burn yourself, or they burn in front of you as well. So, but because with the VPN, I understand these policies, 3 pages long, policy.
You know, we're like,
Oh, that's too bad.
No.
That's not.
Alright.
No, but there is feedbacks there are private.
Sorry for the delay,
And you
let's
can
go
have an
ahead
app where you
and
put the
get
results
started.
in
So
there
I
and
do
help
need
you
to get
diagnose
head
as
count,
well.
because
These
they're
would have
asking us to
private.
keep track of that.
It's not in Apple, of course, right?
And then I think we're down what, to 11 total, so, okay, cool. Because they're gonna ask. Alright, thank you for coming out. We are, once again, this is the Austin Formal Methods User Group, and our goal is to bring together people who are in kind of more of the academic side, who maybe studied this in college or in undergrad or graduate school or independently, with people who are practicing software engineers, and people who are still in academia as well. And there are also some industries where these tools are actually being actively used as well, and so we're trying to hopefully get more cross-pollination, because one of the problems that we've seen in the past is that there is a huge gap in knowledge from the industry side not being aware of what is going on in this field in academia, but likewise there are some very real practical problems that seem to happen sometimes in academia, where these really interesting papers and stuff are created, but then nobody is around to maintain the software, and now we are not able to even reproduce, the artifacts because, oh look, the version of rock was 2 versions ago, and now they've changed a couple of details, and none of the proofs check anymore, and nobody knows why, and we can't even replicate what they were trying to get to, and no one can find them because they probably work at the NSA now, and so we have this issue, and I think the goal, because this is our 1 year anniversary of this group, of the reboot of this group. So our goal is to try to fix that, to try to bridge these gaps here. So speaking of, in this case, we're actually going to be talking about kind of an intersection between 2 different gaps. These are 2 different areas within the mathematics and computer science world, specifically mathematics world, computer science world. And it's kind of an interesting result that seems to be shocking to some folks and completely expected to other folks. And then once you start to dig into the details, you start to get closer to the other side as you get deeper into it. There are the people who find this like, well, of course this is going to be true. The more you dig in, you're like, oh, this was a lot more complicated than I thought. And then the folks who are kind of starting from the, wow, I never saw this coming approach, as you start to dig in, you start to find, okay, actually, like, there's good reasons why all of these things would be true. And so it's kind of an interesting world. But before we get too far into this, first we have to thank, are happy to thank our sponsors. Station Austin, damn it, the LaTeX fairy got me again. All right, I'll need to send that later. But all right, they are sponsoring us with the free space, and we definitely appreciate that. It's a great location, centrally located. It's not convenient for everybody, but it's in a pretty good location. It's familiar to a lot of the software engineers that we would like to get integrated. Occasionally, we've got folks who are from here at Capital Factory, whether they're kind of working independently or with one of the mixed use companies who are based out here. And then we've got a couple of actually formal methods related companies who are working in this area and short walking distance from here as well, and so that's kind of another interesting area. Although some of the other ones in Austin aren't in walking distance. So it's great that they're letting us use this space. They're kind of halfway through a rebrand, I would say, of this part of it, the hosting events and running the co-working space aspect. They're turning into Station Austin, which is going to be kind of seen going forward as a little bit independent from Capital Factory, which will still exist as more of like the incubator side of the house. It's still kind of the same everything. They're just, I think, it seems like they're trying to split the org in half or whatever, so they can operate the two pieces a little bit more cleanly, independently of each other. But if you are interested in getting a co-working space membership here, again, it's a great space if you're trying to make a startup or something like that. We got a link there for you. Also, Zulip. We are happy that we have got a Zulip group. So if you are not on the Zulip, just let us know. We can get you access. It is invite only. Makes it a little bit easier to keep down the spam and everything. Fortunately, we haven't had any so far, which has been great. Unless y'all consider some of the stuff I put. And then, definitely a place where we can share more discoveries and discussions and stuff about further investigations. I know Silas and I a few times have been chatting about like kind of the next steps on some of the things that we've talked about and played around with, and so that's been great. And so if anybody is interested in that, let me know. And I think Silas too, but definitely I can get you access, and I know Rob can. We'll get a few other people admin access. So we're not trying to make it hard to get in. We're just trying to make it so that you have to be here to get in. So or know one of us personally, like if I get Howard, if I run into him, I know he's 100 years old, but if I run into him at a formal methods conference, I'll definitely be sure to get him a link in case he wants to also come and hang in it. Yeah, we'll get to that in a second. In addition, now we've got this landing page. It needs a little bit of work. It's just kind of a dumb landing page, but it's got links. Yeah,
it's super helpful. Like
it's really fast.
I wanted to see what floor we were on today, and I just went to it. It's so easy.
Yeah, exactly. So it gets you to the right places. It's just static links. I think we're gonna modify it so we actually have an embedded YouTube link. It's got a link to a playlist where I put all the YouTube live streams that we've had on there. We've got a link to the Meetup page so that you can see if we change at the last minute where we're going to be. Like this month, we were going to be downstairs, but fortunately we're upstairs this time instead. So you can find out that kind of information as well. Maybe we'll do a little bit more love on this later, but there it is for now. And as a reminder, so formal methods means different things to different people, and there is an ongoing push to try to get us to use the term. So there's a push to try to use more often the term what is it? I should know that.
I had it already.
It's not computational logic, which is not wrong. Automated reasoning. Automated reasoning. And I think that's fair. to me, automated reasoning is to formal methods what kind of the neural networks are to AI, in that it is not in fact the entire field, but it is the vast majority of where interesting things are happening in the field at the moment. And I think that is true for formal methods specifically. But I do like using the term for formal methods, at least for now. I could be talked out for that, but for now, I still go with formal methods because it is, I think, a little bit more inclusive of our friends in the PL world, the programming languages world, which is definitely going to be more relevant to today. All the stuff we're talking about today would still fall into the realm of automated reasoning, but it's kind of at the edge, as opposed to with the term formal methods, it's really at the heart of what we're talking about.
Plus, you could write formal specifications and not use formal automated reasoning. And that's
Yes,
still formal methods.
and that is absolutely true. And that was how I got started, was not using automated reasoning. But then there's the question of like, well, yeah, but why are you doing formal methods? Even if you're doing it by hand, you're still automating it. Like in the traditional, as Turing would say, when he was talking about computers in his first papers, he was not referring to the things that we have in our pockets and on our desktops and everything today. He was referring to humans. When he used the word computers, he was referring to humans. And so that was a kind of automation. It's just not how we think of automation these days. So it's still relevant, but
Okay, the angle I was going to take on that was that you write the formal specification down so you can be clear in your own mind
exactly
about what it is you want to do. And then
Yep.
after that, if you want to use automated reasoning for some of it, you can. If you don't want to, you don't have to, but it's still formal method.
absolutely, and that's part of the reason why I still like formal methods, is because it is a broader subject. Because to your point, if we're literally talking about like acceptance testing, well, okay, we're not talking about mechanized reasoning at all. We're talking about writing specifications. That said, there are absolutely mathematical concerns about how you would even do that, and that's relevant. So, with that said, formal methods are techniques and tools which use rigorous mathematical logic to design, to our point about formal methods being not just automated reasoning, analyze and verify systems with provable properties like correctness, reliability, and security. And so that was the definition we started using 1 year ago, and unless and until we get reason to switch it, that's what we'll probably stick with for now. But yeah. So let's go ahead and get started. First of all, we can go through a little bit of a couple of historical figures. Not all of the relevant ones, but several relevant ones. So first of all, I'm the right kind of nerd that feels like we have to start with Russell. In the early 1900s, as part of this effort that kind of Hilbert helped to spearhead, but Russell and Whitehead were absolutely involved with it as well. They were trying to formalize all of mathematics. They were trying to create this book called Principia Mathematica, or Principia Mathematica, my last name. Yeah. But one of the things that came up while he was playing around with the still relatively new area of set theory, I think it may have been around for decades by that point, but by the scope of things in mathematics, it was relatively new at that time. And he came up with what we call Russell's paradox these days, and it's an interesting thing involving sets of sets. But his proposed solution to this was to come up.
You know what Russell's paradox is? Understand the rest of this?
Not really. Yeah, I actually have a meme that I was going to put in there. I was going to put it in there, but I think Russell's paradox is an interesting thing enough. We can talk about it in a separate talk sometime. But for the purpose of this, it was a problem that came up during his efforts, and one of the solutions he came up with for that was to treat matters of dealing with first order logic. So you're just talking about terms ands, ors, nots, things like that, implications, the basic stuff. Things dealing with higher order logics, so dealing with, you know, properties, and like, you know, having a quantifier, all properties that are true about these kinds of statements, or which allows you to then talk about things like sets of sets or things like that. And then perhaps even higher order logics when it becomes relevant. That by imposing this concept of types, that makes it so you can't mix the wrong type of item together into a statement. So you know that truth has to do with whether or not the mathematical sentence you are saying makes sense. And so they are saying that mathematical statements make sense if they have a particular type, and that is kind of this concept that Russell was kind of pushing for in the early days. I think I should probably point out that the types that he was using are a little bit different from the ones that we use today, for the most part. Sometimes people still play with those, but it's at this point it's more of a historical footnote that that's kind of what got the ball rolling, rather than you really want to go and play with the ones that he did. That said, I still think I want to go get a copy of Principia Mathematica. So it's more of an interesting coffee table book than one that you're actually going to go read from cover to cover. But you know,
is that the one that had a like 600-page proof on why 1 + 1 = 2?
That's exactly the one.
Yeah.
Yep.
All right.
Yep. So next we have Haskell-Curry. So Haskell-Curry was a pretty important figure in the terms of computational logic. He was an American who was associated with several different universities here. You know, MIT. I think he went for undergrad, or no, maybe he went to Harvard, then he went to MIT, then back to Harvard, and then he spent some time as maybe as a professor or something at Princeton before he got his PhD. But when he decided to go get his PhD, he moved to Göttingen. And he was David Hilbert's PhD student. And so that's a hell of a thing. And then what he was working on was Schückenfegel's, I don't know if I probably butchered that name, I'm sorry. Schückenfegel's combinatory logic, which Curry showed was equivalent to Alonzo Church's lambda calculus. It is wild how many of these people knew each other and independently developed these things at roughly the same time. Because, like, if my timeline is right about when Curry was at Princeton, Church was also at Princeton at that time, and so they were like working on these things. I think probably aware of each other, but I don't think they were working together on this stuff. And it was like years later they were like, oh well, okay, it turns out that the things that we were working on are actually equivalent. So it's kind of wild to think about today. But so many of these things were developed independently, right around the same time. Howard, of course, who turns 100 this year, is still alive as far as I can tell. He kind of expanded on Curry's work. So a lot of the stuff that Curry did, he did a lot of the foundational work for what we call the Curry-Howard Correspondence, but he didn't put the last pieces together. Howard did that. Specifically, he combined Genson's natural deduction with the simply typed lambda calculus, which was the key to the Curry-Howard Correspondence. But in order to do that, it depended on the fact that Curry showed that his combinational logic was combinatory logic was equivalent to the lambda calculus, and also several properties about the natures of types side of combinatory logic, and then combined combining that information with Ginson's natural deduction allowed us to get to these separate types of independence. It's also worth pointing out Martin Löf's contributions. A lot of the way that we talk about the Curry-Howard correspondence, probably like the main discoveries were by, Curry built the majority of the foundation. Howard kind of put the pieces together at the top to make the thing work. But the lens through which we look at it, which makes it a little bit more approachable to both mathematicians and software engineers, is probably more the combination of Howard and Martin Löf's work. Martin Löf also did dependent types, which we're not going to talk about today, but it is a thing that we'll probably talk about in the future, and so he's definitely worth mentioning here. So all of this said, I keep saying this type crap. What is this type thing I keep saying? Well, if we're talking about software engineers, you probably have some idea of like what you think types mean inside your programming languages, and you're not going to be very far off in some sense of what we're talking about here. There's a reason why we use that term in software engineering, that we're referring to types, and that actually does trace back to Russell from both sides, and that's part of the reason why I included this, because they diverged at one point, but we can trace them both back to Russell's use of that stuff. So when we're dealing with these mathematical abstractions, very, very basic ones, like what is a point, or what's a set or a line or something like that. And we're talking about very, very fundamental notions of truth in mathematics. It can be difficult to give a definition that feels good, and it's a thing that we talked about back in December when we were starting to play around with the inside of Educara with the proof for De Morgan's laws. When you don't get to assume De Morgan's laws and you want to prove them, you're looking at this proof and you're like, this should be easy, and then you start to play with it and you're like, this was significantly harder than I expected it. Like, it's not hard in the realm of all proofs that exist, but it definitely does not match your intuition with how difficult that problem will be. And it has to do with how
it's not really being easy with proof by contradiction, it's just not using it without was hard. We really struggled with equivalence problem 38, it was a super complicated one.
Yeah, yeah.
Sure,
Well,
distinction is relevant here.
No, it absolutely is relevant. We'll get to that in a second. It's when you don't get to use proof by contradiction. Now you want to go and do something like some of the basic proof mechanisms when you do not allow contradiction. Now you start to get into some problems, and so then you get to something like De Morgan's law. Okay, now you really are in a sticky situation when you start looking at that.
You should be able to prove it without proof by contradiction.
We'll get to that. We'll get to that. So before we get too far into this, so what is a type? And so one thing that's sometimes in both in the mathematics world and in the computer science world, we would say something like a type is, a set. It's a set of possible values that something could have. Well, that's not really a satisfactory answer in this case, I would say, because it's not necessarily the case that two things that have all the same possible values are even the same type. It feels like it should be, but you may be able to, under certain circumstances, you might be able to loosen your definitions of what the types are by coming up with some notion of type equivalence. That is a very deep rabbit hole inside of type theory as well. And so I want to stay away from treating a type as a set and get more into types are patterns. So if you remember when we were doing the lambda calculus a few months ago, we were talking about these integers and addition, and it was really strange that integers were functions. Remember that in the untyped the lambda calculus, which we'll in a minute start calling the untyped lambda calculus from now on, but in the lambda calculus, you don't have integers. You don't have booleans. You don't have anything except for functions. And the functions always take exactly one argument, and that's it. And that's all you have. And so it's like, well, how could you possibly have integers if that's the case? There's literally functions all the way down. And the answer is, we've decided that specific patterns are the integers. And as a result, the way that you use the integers involves things like addition and multiplication and things like that. And that has to do with how those integers relate to each other. That's how you're getting these things.
Right, we're able to define functions such that integers behave the way we expect them to.
Exactly. And it's the same thing with truth values even. You know, booleans don't even exist inside the lambda calculus. What we have instead are very specifically shaped, you know, collections of nested functions or whatever that relate to each other in a particular way. And that is what we have instead of truth values. And so, in this world, you could instead choose a different way of representing them. And we talked a little bit about that with the Boolean definition that we were playing around with in lambda calculus. We were saying the first argument, you know, the truth is a 2-argument function, you know, effectively, and the first argument being returned makes it true, and the second argument being returned makes it false. And it's like, well, you could make a different implementation of truth values where it was the other way around, and then you would have to adjust all of these other things, but you could do that. And that would be an equally valid representation of Booleans as long as you weren't trying to mix and match them. And that's the key, is that those are both valid implementations of the notion of truth, Boolean values, in the lambda calculus. They are equally true. They're just not equal to each other. You can't substitute them. In this sense, the definition of the Booleans which behaves in that particular way, that is a particular type. That is a type of Boolean. There's another type of Boolean which you can create. They are not the same thing, even if they have all of the same members in a certain sense. That, you know, Booleans are, you have a true and a false, and behaves a certain way, or behaves a certain way, not behaves a certain way. All of these things are true. You know, they're true. They behave in the expected way, and yet they are not equivalent because they are different types. The types are the patterns. And of course, as a working programmer, you may be like, well, okay, this is some silly nonsense. At a certain level, like I have integers which are going to happen inside the CPU, and that's a real integer, and it's going to do a thing, and I put electrical signals in there, and crap happens, and then other integers come out. No, you don't. You do not have them. You think you do, you do not. Bytes and machine instructions do not spring forth fully formed from the forehead of a computer engineer, no matter how clever they are. That is not how this happens. They are also patterns. In this case, instead of it being patterns of never-ending functions, of nested functions and things like that, you have patterns of transistors. That's literally what's happening. We've decided this thing is a 1. We've decided this thing is a 0 in exactly the same way inside a physical system. It has to do with the transistor patterns that we have put into the chips. It is the same thing. Now, we have made different choices about what those shapes are in the case of a processor, but that's okay. We've already talked about you can have different choices for how you shape the Booleans inside the lambda calculus. The lambda calculus doesn't change just because you've chosen a different definition of what a Boolean is. And the same thing is true here. You don't suddenly not have a CPU because you made different choices about how to wire it up in your transistor gates. It's still valid. It's just a different pattern. And then you're not going to be able to shape variables from one type of CPU like that, put it in another one, and expect everything to be fine. It will not be fine. Big endian versus little endian is a real thing, and you're not going to be able, unless your processor is designed in a way where it can know the difference between these things, and that's a different kind of type. Now, we're talking about a type where you have concepts like that, and you're keeping track of that kind of information on the chip or on the memory or whatever. Type has to do with the patterns that we're talking about. So, okay, but we're talking about these base types, booleans and integers and such, where that doesn't seem like we have a robust system for describing anything like all this nonsense I was scribbled all over the board. What are we talking about? Well, it comes from once you start getting these, I call it compound types. That is, pardon me, that's the wrong word. That should have been constructed types. Constructed types. Things like functions, you can think of as a constructed type. We're talking about functions that don't have side effects. It gets into a whole other area of logic once you start talking about functions that do have side effects, and we're not going to cover that today. We're just going to pretend for the moment that functions don't have side effects, because that makes today's conversation more sensible. Tuples are another kind of constructed type. You have base types like an integer and a boolean or something like that. You make a tuple of them. A union. I don't know if everyone's familiar with the union type from C. It's not a type that every programming language has, but I think it does a good job of explaining one of these fundamental concepts, in that you don't know which of multiple specific implementations you're talking about. So in the case of C, it's allocating a predetermined amount of memory, and so it's somewhat breaking down this very abstract notion that you have from like a tuple or a function or something. But if you'll pardon the fact that we're talking about a specific amount of memory, effectively, you have a variable, and you don't know which of several different possible types it could be. Now, in C, sometimes we're using that, we're taking advantage of the way that we know that is implemented for things like how specific network addresses or whatever happen to be represented in binary. We know that the union type is going to treat them in a particular way, so we can deal with offsets within this union type, even if we don't know some of the details about how portions of it behave. But in the most general sense, you're talking about an object where you don't know which of several different possible types it could be. And that is one of the concepts that does come up a lot inside of type theory. Again, it's all of the type theorists are probably cringing at that comparison, but there's a reason why they use that term inside of C. It is talking about the notion of the subtype. So a little bit of a note on terminology. Oh, actually, before we get to that one, some terminology from this. So as part of that natural deduction thing, there is this idea in, kind of in mathematics, where we've had all these patterns that we'd like to use to create mathematical proofs, and we've used terminology that we want to use for these things. But in the 19th century and in the 20th century, there was, especially among the people working with types, instead of Zermelo-Frankel set theory, we want to have constructed logic. So you're building up pieces, in ways that don't allow things like proof by contradiction. And so there was a lot of effort to try to build back up the kinds of reasoning that you're used to dealing with in more of the classical logic world. And so one of those is the natural logic. But we're still wanting to take some of the niceties that we've gotten from our 19th and 20th century mathematics. And so that's where we start to get some of this symbols over here on the whiteboard related to constructive logic. And so we have this capital gamma, which is just kind of a shorthand for kind of the context that we have about a system. In the case of dealing with this particular area where we're talking about type theory, we are talking about knowing which variables have which types. So you can think of gamma as being, if you're thinking about like what is the compiler doing, and it's tracking, like it probably has some kind of a lookup table where it knows that each of these variables has this type or this type or this type while it's performing its processing of your code. That's essentially what the gamma is doing in this circumstance. But when you see gamma in constructive logic in general, you can kind of think it's like the union of all the other things that we happen to know. This turnstile symbol, it's kind of like an implication. It means like that implies some of these other things. It means that it yields. There's different terms that they use for that. I think where it's used, they try to split it off from the classical notion of implication because it has some slightly different behaviors. But in a rough sense, you can think of it as being, it's something that we have whatever's on the right because of whatever's on the left. Okay. So if you ever see a turnstile without anything on the left, that means that we know the thing on the right is true, just independently of everything. It's something that's intrinsically true. If you see something else over here on the left, like here, we have this gamma, comma, something else, and then your turnstile, and then something. That means that all the other things that we know that are true in the world, but also this one additional specific thing, or perhaps it's one of the things in there, and we're just calling it out equivalently, depending on how you're framing what does the capital gamma mean. And as I said, the thing on the right is something that we know to be true. These big horizontal line things, this is a thing that came from the natural deduction world. And it is, you have a couple of things, up here above the line, which are things that you know to be true ahead of time. And then that line implies, basically. And so you can think of this as when you add together this piece of information, you know that, capital gamma, something about the world tells us that the variable A has the type capital A, and also that, so the space means, plus or whatever, also that everything we know about the universe somehow gives us that the variable B has the type capital B. Having both of those things be true at the same time gives us this other thing. It tells us that we have enough information in what we know about the universe such that this ordered pair AB has the type A product with B. That's what it's saying here. So that is what natural, kind of the terminology that natural deduction gave us. Natural deduction was this attempt to try to bring all of these ideas that we're used to dealing with in the classical world into this constructive logic world. And so it's combining these ideas that we had, implication, eliminations, and stuff like that we've always had in the classical world, and trying to give justifications for this in this constructive logic world, along with new symbols that give us this stuff. And so we'll get to what specifically they are in a minute. But so when you see this stuff, just remember, when you see capital gamma and then a bunch of turnstiles and you're like, oh my god, what the hell is happening on this piece of paper? It's like, okay, remember, capital gamma means things we know about the world. Turnstile means somehow from the things that we know on the left, we get the things on the right. And when you see this big old line, that means that all of the things above somehow give us all of the things below. all the things above are true at the same time, or we have them in some sense from constructive logic, then all the things at the bottom we also have. So now, curry. This is a thing you may have seen if you've written a variety of programming languages. This idea where you have a function which has a whole bunch of arguments, and you're taking one argument at a time off of the front. We saw a little bit of that when we were playing around with the lambda calculus, kind of implicitly, where we were taking a function that only makes sense to have multiple variables, but in fact we were just chopping off the front variable over and over again until we were resulting in a function that only has one variable. This approach has been used for a long time before Curry, but Curry used it so much in his papers that now we call it currying. And here's an example of the pattern and a little bit of the symbols that you would see associated with it. So up here at the top, this is not a Curry version of add. And so its type, the type of this function add2 is this. So it takes two integers, int crossed with integers, this product type thing you see up here. We're taking two integers, and as a result, this arrow thing, it's going to return one integer. So it is somehow a function, that's what this arrow is essentially telling us, that takes two integers in a particular order, and it gives you one integer back. That's what this type thing is telling us. And here's how you would implement it. So in order to make it a little bit clearer, we're not using def. It's Python, but we're not using def. We're using lambdas everywhere just to make it so that you get something equivalent looking. Because if we went with defs, it blows the hell up, and it's hard to follow. The lambdas make it easier in this one specific case. I assure you. So we've got a lambda expression inside of Python, their version of it, where they'll let you throw in multiple variables at once. If you're not familiar in Python, you can put how many variables you want. It doesn't look very much like lambda calculus, but that's all right. That's all right. We'll let it pass. And then, so you're taking two variables in, and you're adding them up together. That's what you would expect it to be. And that's how you would call it. You add two, and the curry version of the same function. So this is, you can see this is going to do the same thing, but the way it is set up is different. So this one, this version of we're going to add2 underscore curry, C-U-R-R, and it has a very different looking type. So it is something which takes one integer. So it's a function which takes one integer as its input, and then it returns another function, and that second function that it returns takes an integer as an input and gives you an integer as an output. And so you may have seen this before if you've done like a lot of JavaScript programming with closures. Closures are basically doing currying in a very particular way. And so in this particular case, we have this double lambda thing happening here. And so what is actually happening is when you call add2 curry and you give it one argument, because you can only take one argument, it will give you back a function, a new function, which is a lambda, which will only take one argument. And so we're going to call that intermediate function this add2 curry intermediate. Not a very nice name to look at, but it gets the point across. And then after that, we're going to call that function that came back from us with the argument 2, and then that's the sum that we were looking for. And so down here, you know, this is how you would probably actually run it instead of doing this intermediate thing. You do add2 curry, and you give it one argument, and then immediately you don't even give a name to the intermediate function. You just call it immediately, and you get the second one. It's usually when you would do it. If you were ever need this pattern inside of actual programming languages, that's probably more how you would call it. So you're like, okay, well that's an interesting example. Well, why the hell did you make it add2? Why didn't you make it like add of an arbitrary depth? That seems like a thing you should have done, Charlie. What are you thinking? I'll get to that. There's a reason I didn't do that. So, next, going on to the simply typed lambda calculus. So, if you remember with the lambda calculus we talked about before, it's like this very simple programming language. It's kind of the first programming language, you know, the simplest programming language is what we said last time. I guess that's arguable, but more or less that's a way you can think about it. But from now on we'll call it the untyped lambda calculus, and you'll see why. So the syntax, just as a reminder of the untyped lambda calculus, you've only got three different things you could possibly do. You got a variable name, which is just like this string. It's just like, used to always be a letter, and then back in the 30s, or 40s and stuff, they were really, really concerned. There's only 26 letters. What happens if you want more? And it's like, dude, add another letter. It's fine. And people, you know, they didn't think about these things the way we do now, where it seems like something we would just gloss over and not worry about. But they were really worried about this. They have special terminology and everything for dealing with it. Abstraction, where you have the symbol lambda, which is where the name of this thing comes from, this untyped lambda calculus. You have the character lambda, followed by a variable name, followed by a dot, and then another expression. So it's this whole thing again. It can be any of these things inside of there. And then application, where it's just two expressions set next to each other. We can also add parentheses in a bunch of places. It's a good idea to add parentheses to these. They get way out of hand really quickly. Sometimes I think it is in fact impossible to represent unambiguously some of these results without parentheses, so definitely you want to add them. You can always add them. I guess you can't add them between the lambda and the dot, but for every other circumstance you could add them. So that was the syntax. So anything, so it's remember, for untyped lambda calculus, literally anything that matches that pattern is a valid lambda expression. Anything. So now let's get into the semantics. So alpha conversion, as I mentioned, we're talking about, they're really, really worried about variable renaming. And it does get to be a really big, tedious problem if you're not careful, if you're trying to do these things by hand for some reason. So I will define for here, just to make things clear, when I'm saying alpha conversion, I mean that you're going from the most nested to the least nested, and you're just picking a different variable name and changing all the instances of the variable name inside of your lambda expression. All the instances of it inside of the expression that's part of the abstraction there. You're changing all of those to whatever the new name is, just so that there's no possible collisions. Okay, that's what I'm going to say, because there's all kinds of nuances and more tricky ways you can say that. What I'm describing here is equivalent to all of those things you're doing right now, so it's fine. Same thing with the beta reduction. So it's really specific. It's when you have an application, so you remember, application means two expressions next to each other. That is what application means. You have an application where the first sub-expression is an abstraction. Going back here, abstraction is that lambda thing. So it's an application. The first one of those two things is an abstraction. Okay. And you've done all your alpha conversions already taken care of. Don't worry about any of the alpha conversion. That crap's already done. Okay. Then what you're going to do is replace all copies of the variable in the first abstraction. So that, remember we said that the abstraction is the first expression in an application. So you're placing the variable in the abstraction inside of all the copies of your expression from the abstraction, with the unmodified second sub-expression. So you're taking that second expression and replacing it with the first one. This is just the lambda calculus. I'm just trying to quickly describe how it works. That is what beta reduction is. And as we pointed out, beta reduction is the thing that makes the computers go. It is the thing that gives us Turing completeness from the system. That is where all of the magic is happening, is inside the beta reduction. It's a really simple and very specific niche thing that we're describing here. It doesn't seem like it's very complicated, and yet that system is what makes it so that lambda calculus can represent any computable thing there is. The untyped lambda calculus, that is. Get to that. But as we saw, beta hell is a thing. Oh, I should have put more space between that one and the two. We ended the lambda calculus talk with showing what beta hell looks like, and we tried to do a beta reduction on the expression 1 plus 2. Okay. The thing is, 1 plus 2, because of what integers are and what plus is, they're just functions. It's all functions all the way down. That is a syntactically correct lambda expression. It just doesn't mean what you think it does. The plus 1, 2 means what you think it does. The 1 plus 2 does not mean what you think it does. And so when we did a beta reduction, it turned into this giant pile of nonsense. It had no meaning. It was this weird crap. It took forever to run. It was totally inscrutable. We could not figure out what the heck it meant.
And that second one, I'm using 1 as the function that I apply to the arguments.
Yes, yeah. That second one is you're running the 1 function, which is taking as its argument the plus function. That is the argument we're giving to plus and to 1. We're telling 1, I want you to go run plus. And so that means, okay, well then I will run plus 1 time. But the way that it unpacks that normally would be fine, except that it's not fully defined with how the plus worked. And so it actually unpacks it, I would say wrong. It's not wrong, it's just not the way you expected it to. What 1 does to this is not what you expect.
It was fine if it was small talk.
Yeah, exactly.
Because you literally did send the plus message to the 1.
Yeah, you sent a message in that case, but that's a difference. Yeah.
Because it's untyped, any of these are meaningful. It does something.
Yeah, it does. It means
It just
something.
doesn't have a-
It just doesn't mean what you think it means.
So you're basically saying like 1 is a function, 2 is a function, and plus is a function.
Yes.
They're all functions, and you're basically operating in order.
Yeah, that's right. And so what happens when you evaluate that? You can go try it on what is it, lambdacalc.dev? Was that the one that we were using? It's interesting. It's not. It doesn't mean what you think it means. It gives you this.
There's a very cool video of
Yeah.
some guy that actually did the numbers graphically with bars on the bottom, and he does all these videos with how can I say? So he devised like a line-based approach to represent lambda calculus.
Oh yeah. Yep.
A line-based approach?
Yeah. So
Like a tree diagram?
almost like a tree diagram, but it's almost like, but it looks like F's and you know it looks at how should we?
Yeah, I think I got someone here who knows a little bit about that too.
Yeah, that's a good very cool.
So, as we mentioned at the tail end of last time, wouldn't it be nice if we didn't have to worry about that beta hell? Wouldn't it be nice if we had something that would keep us from having to run into this problem? And so, sounds like we're all this type stuff we've been talking about. So for the simply typed lambda calculus, we're imposing onto the lambda calculus, or maybe imposing onto it is the wrong way to put it. This is a new programming language, effectively, where it's starting with the same lambda calculus notions, but you can only perform beta reduction if the types are the ones that you have indicated that you're looking for. And there's ways to encode that. I think the details of how that works, I debated whether to include that. As I see we're running a little bit lower on time, I think I made the right choice in cutting that. I thought about going into all the details of how that works. I I decided to cut it, and I'm glad I did. But we'll just say that you have this notion of you can enforce it from the language itself. The simply typed lambda calculus is a different language than the untyped lambda calculus. It's very similar, it's related, but it is a different language because it behaves in a different way. Specifically, it has to do with how the beta reduction works. That's what's happening here. It's going to only apply if the things work. If it doesn't apply, then it will not run. So, in addition to our notion of what is an integer, which we now have the ability to represent that as this particular pattern. Integers are things that look like this. Booleans are things that look like this. We're actually telling the language these things. It doesn't necessarily know what integers and booleans are. It just knows if I see this pattern, I'm supposed to treat that as a special thing, which is different from this other special thing, which has a different pattern. That is what we're saying. So we have these base types that we're dealing with, but we also have the canonically constructed types. Product types, sum types, and function types, which we have here. Okay. So, okay, well, let's transition to this real quick. So, let's keep the question of how the base types work here. We'll just kind of leave it glossed over. As we mentioned, it's important to remember that there are different possible implementations of integers or natural or booleans or whatever that you could have inside of the lambda calculus. And it has to do with the patterns that you're
Other
using.
ways to do integers.
What?
There are other ways to do integers.
Yeah. Again, they are going to be similar in certain ways, so it may not be as novel as having the two different Boolean implementations, but seems more surprising. Your different ways that you implemented integers probably wouldn't be as surprising to you, but yeah, they could be done differently.
But
Anyway,
I assume you can't identify the type based on the shape, right? In other words, you have to say that this is of this type. You can't just look at it and go, this is a function from booleans to booleans, or this is an integer. Right, just by looking at the shape of it, you can't do that.
yeah, you can't. Okay, yeah, I should have. We're not going to after the fact decide whether something is the right type or not. We're not going to be given a pile of functions and say, oh, that looks like this shape or whatever. We only get to accept whether or not something is of the right shape because we know how it got there. In a sense, we're doing it with, and that has to do with how the beta reduction is implemented. But for the simply typed lambda calculus, what we've got is the beta reduction implementation is saying, I will only accept your evidence that you have the right type if we have provenance of how you got that type. And so it still has to do with the right shapes, but it's only going to believe you because of how it got, why it, what is the path of things that happened that lead it to believe that you got the right shape. So, when you combine your types into the product types, the sum types, the function types, we'll look over here. So these like A's and B's and stuff up here, I've got the capital A's and capital B's. You can think of those as being integers or booleans or something like that. Whatever the type is from the simply typed lambda calculus, whichever implementation of integers you want, whichever implementation of booleans you're looking for, that is what these capital letters are referring to. Okay? And so here are the constructed types that we can make from the base types. So this product type is when you have, this notion of some kind of like an ordered pair of integers or something like that. So you have two different integers, or maybe you have an integer and a boolean for some reason. Okay, that could be a product type. And so the way so you got your product type, which is this like word pair thing. You've got your union type, this sum type, which
One or the other.
that's the one that's a little weird. You'll have to get into some nuance. But then you get your function types, and that one probably behaves in a more familiar way to software engineers. In that it's you're given something of a particular type, and somehow that is transformed into something of a different type. Maybe A and B are the same, and so it's a map from integers to integers. That's fine. And it's also worth pointing out that all of these types, these A's, these B's, these C's and stuff, can themselves be the product type, or the sum type, or the function type. So you can have a function which returns another function, just as we saw earlier. That is, in this case, your A would be integers, and B would be a different function type from integers to integers. For example, for that sum one, or for the sum two we had earlier. So, yes. Okay, what is this? Yeah, and there are other ways of approaching this than just these simple ones that we're talking about here. I am not qualified to go into all the different ways to deal with type theory. That is a very deep field that is very interesting, actively researched. Love to have some talks on that. If other folks want to present on it, I will probably present some stuff in the future on some of this stuff, but I'm definitely still learning. That is a very deep well. So now, before we go any further, this stuff has to do with the natural deduction things we're talking about. So remember when I was saying that one of the things that came about is an attempt to turn this constructive logic thing, where we don't like to have things like the proof by contradiction. And so instead we are using this notion of trying to build up the things that we know to be true a piece at a time. This approach to coming up with proofs, which is called natural deduction, involves these products, it involves these sums, and it involves these functions of various kinds. But as it turns out, we can actually map all of these concepts from the natural deduction directly into the types that we use for the programming languages that we talk about. At least specifically, natural deduction is the same thing as the simply typed lambda calculus. So these deal with the simply typed lambda calculus. So the particular implementation that we're talking about of the modified beta reduction, where you can impose the behavior of a particular plus can only operate on integers. So it is the integers plus. So you implemented plus in a way that only accepts these two integer functions. So that means that in order to be able to run plus on them, you had to have constructed the integers by using the special integer creating things.
So now, if you did that, does the function return an error? Did you have an error condition?
No, in the case of the simply typed lambda calculus, the beta reduction just wouldn't apply. In a sense, it's undefined and it won't run.
It just remains on, like, fully expanded or whatever. Yeah. It just remains as an expression. You cannot use.
Yeah, yeah. That is one of the ways that you can approach it. Yeah. So there's different ways that you could model it, but yeah, that's one of the ways.
I have just one other question. So you're touching it a couple of times. When you say you cannot use contradiction, I get that a while back. It might have been difficult to think about contradiction as a way of proof. But I suspect that's not a thing anymore. Like modern proof languages don't have that issue anymore.
that gets back into the
Okay.
type theory. So it is still a thing, but the solutions to that are complicated, and they're varying depending on which system you're looking at. And so, no, we have, in one sense, we have not solved that problem at all. And in fact, we know we can't. Some of this absolutely gets right back into Gödel's incompleteness. On the flip side, we have come up with increasingly sophisticated workarounds
Yeah.
that get us to the point where,
It's not practically.
yeah, it's practically irrelevant in most circumstances.
Yeah.
And so,
It's a matter of finding the right expression or the right formalism to use for the.
that's
for the
correct.
input.
Yeah, yeah. But that's part of the trick, is the way that we know we are able to do that is actually in part because of this
Oh,
material,
absolutely.
the Curry-Howard.
It's a step from the.
Yeah. But we'll get to that in a second as well. So with the Curry-Howard correspondence, where we're saying that the simply typed lambda calculus and the type theories that we're talking about, the type theory we're talking about with the simply typed lambda calculus, and the behavior of this natural deduction system are the same. In a sense, propositions in natural deduction, because you see, these, we're talking about types here in this representation, but this is exactly the same way that the natural deduction system behaves when you're dealing with propositions. So you're like saying something like, if you're trying to work on Euclidean geometry or something like that, then these would be properties which we believe to be true. You would have a form of introduction for saying that both of those properties are true at the same time with like a logical and. And so with the natural deduction, you're able to use this kind of a setup to say that A is true from the things we already know, B is true from the things we already know, A and B together are true from the things that we already know. That is where this particular behavior comes from. So we'll go into some of the specifics here. Conjunctions as the product type. So as we've already pointed out here, when we have like, you know, these two different types, we've got this, maybe two different integers, or maybe we've got an integer and a boolean, or two different booleans, or whatever you want it to be. Maybe it's two different functions. Like I said, these types could be any of the valid types, whether they're the base types or constructed types, or you know, constructed types. It wouldn't matter. Anything that would be one of these types, we could construct like a tuple of them, you know, an ordered pair or whatever. And so we represent that with this multiplication symbol, since it's like the Cartesian product in mathematics. It's the same thing as P and Q, being the idea that two things are true at the same time inside of the natural deduction system. And I keep making that distinction because here in a second it's going to start looking so much like the classical logic you're used to. But at least for now, this behaves exactly the way you're used to. P and Q, they're both true, they're both completely true. That's not really a question that we're having. And so that is, that's what we're dealing with. And so one of the tricks that the natural deduction system came up with was for each of these different types of constructed systems, you know, the constructed types in this particular case. We have both an introduction rule and an elimination rule, okay? And so in this case, you've got the product introduction rule. And so if you have, when we're dealing with the types version of this, which I'm saying is equivalent to what is happening inside the natural deduction version. So we'll stick to describing it in terms of types. If you have a variable of type A and a variable of type B, whatever the type A and type B are, you have a variable of type A and a variable of type B. From that, you can construct an ordered pair of AB that you know will have the required type of an A cross B. So, not surprising from the perspective of a programming language. If you have a variable of a particular type and a variable of another type, and you put those two things together in an ordered pair, then the type of that ordered pair is this Cartesian product. And also, product elimination. In this case, we split it out into two different ones. There's another way you could formulate it where it's just one. But in this case, we're going to say you've got product elimination on the left. And so if you have an ordered pair, and to be on the safe side, we're not even going to call it AB. We're just going to call it P. P is at some point we had P equals AB. We don't necessarily know what the variables are. From that, you can definitely get a variable of type A, and it's from extracting the thing from the left from this P, and so that's this assembly you got. So it's like the first item. So if you were thinking of this as a tuple, it's like a two-order, a two-size list, then you would get the first item in the list, item 0 if you're dealing with a language that deals with that way. And the same thing with the right elimination rule. So if you have something you already know is an ordered pair and you're trying to get the thing on the right, you can get the thing on the right by just asking for it.
Just to belabor the obvious, this clearly maps to the whatever conjunction rule and the educator proof system thing, or logic.
Exactly.
Yep. I looked into Morgan's law and I got my head thumbs up right now.
Yep. So now, let's skip over this middle nonsense for a second and let's go over to the right-hand side. Implication as functions. And this was the thing that was the most surprising to the mathematicians at the time, I think, was that it worked as well as it did. So if you have gamma, so all the things that we know in the universe, and you have a variable A that is in the type A, and from that you are able to get B in the type B. So again, B doesn't already exist, but somehow we're able to derive it from this information. That is enough to say that we have this lambda expression, lambda x dot B, which has the type A gives us B. So that means we're able to create a function which takes A's as input and gives us B-like things as output. Specifically, this B is one specific B.
The symbol on the top is different from the implication operator between the A and the B. On the top, the one in the middle.
Oh, that's the turnstile one.
Okay.
Yeah. So now that seems a little weird. You see we have this alpha on top is in type A, and we don't see shit about alpha down here. What's happening? And it's like, well, do we even need that then? Because we're down here, we're not even talking about it, so why do we even have this? Essentially what we're saying here is, we have to know that it is possible for something to have the type A. Because up to this point, we haven't established that yet. So, if we know all the things in the universe, and that it is even possible to have a variable, an actual variable that has the type A, if that information is enough to give us type B, then we have enough information to have a function which maps A type things to B type things.
So do you actually need that dependence then? In other words, it's not two separate assumptions. It's not gamma, from gamma you are able to conclude that A is a type. Sorry, alpha is a type.
Yeah, we're not.
And then separately from that you conclude something about B. What you're saying is that it might be the case that in order to conclude something about B, you need to know
that A is
possible.
And so that
kind of interesting.
Yeah, so that's the interesting thing here is that means that this is extra assumptions. Down here, we have this function. We don't even know if it's possible to call this function. So that's the
Like a
important.
precondition.
Yeah. it's a precondition. So you don't get to call the function in the simply typed lambda calculus unless we do have something we can pass in. But that doesn't keep us from making the function. We can make a function that just could never actually be called. But without knowing that if we were to assume that something could possibly have that type, as the terminology we would use is that type A is inhabited. That means that it is possible for something to have that type. If we don't know that it is possible, then we don't necessarily know that this function will ever run. But if we assume that it is possible, and then that's enough to give us that we know that it is possible to have some variable of type B, then we can make a function, which if they gave us an A, then we can give them a B. So it's a little weird. But that gets us to that inhabited types thing that I mentioned. Well, what is that about? Well, remember I said that these types are equivalent to propositions. So in a sense, if we have a variable of type A, that means that we have a proof.
Like abduction.
Yeah, that means, like, you can think of A as a theorem. The type, as weird as it is, the type of A, the type of an integer. That was not an interesting one, but let's say we had some type.
It's just the only thing that feels funny is that it's not bound. You know, that there's something that is left unbound.
Yeah, it's left unbound. Yep. We did. That's the weird thing. It doesn't have to be bound in this particular case. It's weird, but it doesn't in this case. Because normally, you know, certainly from classical logic, like that's a red flag, is that if something's unbound, like what are we talking about? And from constructive logic in general, we think it's even worse that something would be unbound than in classical logic, because at least with classical logic it's bound, but we're able to introduce it as long as we give a bound. And classical logic and constructive logic, you can't just introduce stuff willy-nilly like that. You always have to have a justification for everything. So it's strange, but that's the situation. If it was possible for some value to exist for A, which we don't even know, but if we're saying that it was possible, then if that is true, if we assume that to be true, giving us that then it is possible for something to have value B, then we can create a function which gives us from A to B.
Yeah.
So it's weird. That's the function introduction rule. We also have a function elimination rule. So if we have a function which takes us from A's to B's, and we actually have something that isn't A. Like we have, in the case of natural deduction, we have a proof of a property being true, a proof of a theorem. We have a proof of it. Or in the case of a programming language, we just have a variable that has that type. It is the same thing. Then that is enough information to know that we can take that variable of type A, put it into the function f, and then that will give us something of B. And why is that relevant? Well, again, going back to the natural deduction thing, that means that knowing that some kind of a transformation on a particular theorem, in a sense, if we take as an assumption, assume this, then we know something else is true. And we know that this thing is true, now we have this. Does that look familiar? It is the same thing as an implication elimination rule. And that's why. Function elimination is the same thing as implication rule, implication elimination in this logic. And it's not that it is similar. That's the interesting thing that Curry-Howard gives us, is they are exactly the same thing. They behave exactly the same way. And then we get into this awful mess. Thank you to constructive logic.
Which is the same thing as modus ponens, right?
Yeah, that's modus ponens, yes. Yeah. That is the version of modus ponens that exists in natural deduction, and it also now exists in the simply typed lambda calculus. So now we get this weird thing. Okay. So disjunction types. Well, we have an and type, and we have an implies type. So shouldn't we have an or type? Oh boy. Well, that's the thing, is it turns out with constructive logic, we're getting rid of the law of excluded middle. So you can't have P or not P. You don't just know that to be true. Not a priori. You could establish something like that to be true, but that is why you can't use proof by contradiction inside of constructive logic. Is because just because you're able to show something isn't true doesn't mean that the opposite is true.
Plus, we haven't introduced negation yet.
Did what?
Plus, you haven't introduced negation yet.
Yeah, we haven't introduced negation. I didn't end up covering negation with this one because it means something. What it means for the types is a little bit different. So in this case, the sum introduction rule is a little weird. So it's like, okay, if our universe yields that there's a variable A of type A, now we have this left introduction of A has type A union B, A plus B, and then we've got, if gamma gives us a variable B of type capital B, then we have the right introduction of A plus B. It's like, oh man. Again, like, this doesn't feel very satisfying to people who are coming from the classical logic perspective. Mm-hmm. And for example, like, you know, if we were to try to think about this from the perspective of a C programmer, these sum types are like the C's version of a union, but when you're trying to evaluate those sum types, it's kind of like doing short circuit evaluation. And so that's why you can't, just because you have, you know, A or B, just because you know you don't, you know, you can eliminate A, oh, we don't have A, that doesn't necessarily give you B. In classical logic, it would give you that, but we have specifically denied that in this natural deduction.
Just because it's all just function composition.
That's right. That's right. And so that feels very strange and unnatural to us, but the trick is, the important thing to keep in mind, that is exactly the behavior of the simply typed lambda calculus. And that's one of the things that we figured out, because the way that they constructed the beta reduction, it actually behaves exactly the same way. So what does this give us? Well, this gives us this really interesting thing. If you're able to construct a type-checked program, that is equivalent to a proof of something. So in a sense, when you're building a program, you are essentially constructing a new type. It is the combined type of all the information you have given it. You know, so if you have two integers and then that gives you another integer, well then that has to do, it's actually giving you this function here. You know, it's got, you know, a product integer gives you an integer or something like that. That is essentially what you're doing inside of the simply typed lambda calculus. Your program, in a very real sense, can be reduced to its types. Okay, it's a little bit unintuitive at first, but again, try to think of it as this is not like a normal programming language, this simply typed lambda calculus. It is more like the type system of the programming language that you're used to dealing with. So that's why it's kind of interesting for certainly the simply typed lambda calculus, but for a lot of other programming languages, when you construct a program, there is an equivalent theorem that you're able to prove in the equivalent logic system to your type system. Okay. And so the fact that all the variables can exist you are proving a theorem. Now, that's usually not what you're trying to do with when you're creating a program. Like if you're like, you know, oh, I want to make a user dialog box. Like, okay, well that's not, that's probably not like a super important mathematical result. You know? But yeah, well, yeah, even once we address the side effects and stuff, it's still not going to be a very interesting mathematical result. Like, but it does give you the beginnings of being able to address these things in that way. And that's where you start to get into these interesting approaches. You can start to use the tools from either side to inspect each other. One of these things is when you're dealing with these strange alternate logic systems, you can think of them as strange alternate programming languages. And so if that is helpful to analyze a logic system, you can look at it as a programming language. If it's helpful to understand a programming language, you can look at it as a logic system. And so you can start to get into these things. Church of Logic is this really interesting podcast as well. Type Theory for All shirt I'm wearing here, but there's also Church of Logic, which is another interesting one. Unfortunately, they're on Spotify, but it very fascinating discussions on there. There was several times they've discussed like the equivalence between specific type systems and specific logic systems, which has been very interesting. So if that is an area that you find intriguing, I would definitely give it a listen. You also have, in addition to being able to try to look at, logics through the perspective of a computer science programming language, and so that can help you get more intuition about the programming language, about the logic. You can go the other way around, and so you can analyze your programming language from the perspective of logic. And that's absolutely related to the stuff that we were talking about like last month, where we were trying to look at a concrete semantic for a programming language that we were introducing. There are aspects about the way that system behaves which we can analyze with pure logic of the logic system that matches the type system that we are looking at. And so as a result, we're able to use one of these tools like Isabelle to reason about the logic underlying the programming language itself. Which kind of gets us to one of the weird distinctions between the programming languages that we use on a daily basis and some of these interactive theorem prover languages, for example, like Isabelle and Rock and whatever. These interactive theorem proving languages tend to not be Turing complete, which seems strange to think about. Like, well, it's a programming language that's not Turing complete. Well, that feels bad, but remember, it's okay because we're not trying to use the type system inside of your compiler to perform complex calculations. The compiler is producing a program which will run to produce complex calculations. Remember, Turing completeness says that we have things like the halting problem. We don't know how long it will take for your program to finish, if it ever does. Well, that doesn't sound like a good compiler, does it? Like, you run the compiler on your code and you don't know how long the compiler is going to run, or possibly if it will ever terminate. That doesn't sound great, but that's literally what we're talking about here. And so the type system that you're imposing on top of your programming language is itself a kind of programming language that is not Turing complete.
I mean, I don't know if you've seen this, but I saw a couple of ideas for type languages. I think it was on Isabelle, where this type language was used to be able to do fixtures for testing, where you would be able to automatically create a lot of the structure of the execution itself, where the actual code that you would write would be just the minimal part of the code, because everything that calls the code already was including text fixtures. And another The part that I saw was also interesting was where there was some observation that could be done that would give some invariance that you couldn't get through type systems.
Yes, yeah.
That's another interesting.
Well, and it also gets interesting when you get kind of the combination. So there was from a C, which is a system that can be used to analyze C code. And one of the things that you can do is to make statements where you're trying to prove properties about the behavior of your program. Some of the properties that it will allow you to express cannot be evaluated at compile time.
Yes, yeah, that's what it.
But what it will do, if you ask it to do so, is it will augment your program to add a runtime check system. So it will automatically generate the code to do this, and then at runtime it will check to see if whatever assumptions you had still hold. And so it will actually try to generate a minimal version of what it has to do. What are the things that, if this thing is true at runtime, then I know that the whole proof is still accurate. And so rather than trying to prove it at runtime, it tries to reduce the compile time proof to the minimal thing it has to know at runtime to know if it's true, and inject that. And so they do that. I think that was one of those things that I think Airbus introduced that into for MSC because they wanted to use it for doing some runtime checks of some of their avionics systems. So that they wanted to, belt and suspenders. They wanted to know both that they know it's true ahead of time, but they also want to know that it's true in the face of something like memory degradation or certain circumstances.
And what's questionable to me is that if you think about how much effort is put into writing some tests that are unit tests or complex text harnesses, if you're going to get that by just building the thing.
Yeah.
I mean, there's a question of maybe there's value that already there. It's not.
And so it's this interesting problem. So we say that some of these languages are not Turing complete, which feels wrong, but again, no, it's fine. You are not going to go and try to perform some interesting calculation inside of Isabel or inside of Rock. Now, you might reason about a different program which does do that, and that's what you're looking for, generally speaking. But it's also another one of those details that, in fact, the type systems that, the behavior of these languages is more complicated. These type systems aren't actually that simple. So one of the things that I'm glossing over here is part of the reason why it's not Turing complete, and Turing was actually the one who showed that it was not for the simply typed lambda calculus, is that you can't have indeterminate loops inside of simply typed lambda calculus. All loops have to have a finite length. They only run. Yeah, exactly. And so you can't have, because of the way that you're constructing
Numbers are constructed as a function. So
yeah. And so you can make them arbitrarily high, as however high you want to make them, but they are not infinite.
You're going to run out of paper. No?
Yeah, exactly. And so that's the weird thing about these things. And so earlier, when I mentioned that, well, why don't you just make, this Python definition of a curried addition like the way that I was doing it? Now, you could do it in a different way, and then you might get something that would be kind of similar. But the reason why you can't make an infinitely deep curried addition inside of Python the way that I was doing it has to do with the type system of Python, which is not Turing complete. The type system is not Turing complete. Now, it turns out you can't actually have infinite, again, it gets into areas of type theory I'm less familiar with, like exactly which type system is Python actually using. I don't know. It's probably more sophisticated than the one than the simply typed lambda calculus. I don't know which one it is in fact using. So it may be able to do it by some other means, but it certainly cannot do it the way that I was showing up there.
For me, the aha moment with this stuff was when I realized that for hundreds of years, maybe thousands of years, you did proofs, in a sort of natural deduction style. They had axioms and you proved stuff.
Yes.
So what was interesting to me about this is that this is a completely different way of doing proofs. Now you construct a function of that type, and that's your proof.
Yeah, exactly.
So that to me that's just a, you know, that's just, to me that's incredible.
Yeah, yeah,
You know.
it is very powerful, and again, it's really helpful when you're dealing with alternate logic systems. So if you're like, well, I don't like the way that proofs in this kind of a system work, I would like to come up with a different one. In the past, I think mathematicians would have just like, you know, kicked you out, like, you know, you're too drunk, go home. Like, we don't wanna talk to you about this silly thing. Now, that's a totally legitimate thing that you could discuss, because it's not some totally ephemeral, we have no way of even checking what you're talking about, who knows. No, we can construct this thing, we can go try to build a programming language that looks like that.
So what would be a good example of a proof that was done that way, even if it's not like the first proof that was made, but even if it's simple thing that actually was proved this way and it turned out to be much clearer?
Behaviors of a particular system. Yeah, so there are a lot of alternate, it definitely gets into the type theory stuff, where most of the good examples come from. And so there are very specific type systems that we could be looking at to know, you know, compiler behaviors and things like that. Is this behavior, is this compiler optimization safe? Will it actually?
Like for example, I was just thinking even something simpler, you know, like is there like a proof of the Pythagoras theorem, you know, you could do it. Not, I mean, just something like that just shows the power of doing the type, proving by the type, not necessarily proving.
Yeah, so yeah, getting kind of mathematical proofs that we're used to and seeing what would a program look like that is actually showing that, for example.
Yeah.
Yeah, we,
I don't know,
that's definitely a thing.
to think about it.
I should have put an example about that, I'm sorry.
Oh,
That's a good point, I should have done that.
So the most trivial example I can think of is, and it's a completely trivial example, right? So if you've got, if you want to show that P implies P, right? That's equivalent to showing that the type P arrow P is inhabited.
Yeah.
And for that, you just, the ID function will do it.
Okay.
So if you're able to build an ID function in whatever programming language.
Right,
So now
exactly.
if you have a type system where you're not capable of doing that, then
Yeah.
you would be talking about a logic system that wasn't capable of showing a P implies P.
I can come with a hello world example of the theorem A implies B implies A. You know
Yeah.
that one. And that's equivalent to like a constant function, where it's like whatever comes in.
Yeah, you could do it through a function introduction, yeah. Yeah, inside the simply type planning calculus. Now, if you're talking about a different system, then maybe you could or couldn't do it, depending on what the system is. We are running very light on time. But yeah, as my closing remark, treating mathematical proofs like programs can make them more accessible, and likewise, treating programs like mathematical proofs can make it so that we can better understand the behavior of the program.
Cool.
If your Haskell compiles, is it correct?
Yeah, most of the time.
Well, in a certain sense. It is type correct.
So, you're gonna like it. It's an awesome video. Sure, everybody should post it on the chat.
Yeah.
Hey, you bet.
Oh, yeah, oh, yeah.
There's an event on
But yes,
the
please post it on Zoom.
But, yeah.
Oh, yeah. If anybody needs access to the Zulip, please let me know.
Okay, fine.
I thought you said
I think it might be right. I'm gonna check it out.
They're having a don't conference. Well, what is that?
I've seen this, like, these videos.
Like more foundation work.
Thank you.
So,
Okay,
stuff like
certainly, if anybody has ideas for process, please let me know.
There's a
But also,
there's a
I'm
project
gonna try to go.
national number game.
A couple of professors
by people who
indicated
Saturdays.
they
are
were willing to
actually
talk.
like they've already formalized of most recent graduate.
I never heard of
Yeah,
that.
counselor.
Are you associated?
Yeah.
But I met them, and so
Yeah.
we chatted, we get along.
I was looking for a book in the geography, but I couldn't find.
Yeah.
There's a book that would be great. If I could find, the history of computational science.
So they're actually, they have set it up such that
There's a comic
basic
book,
like natural number theorems using Lee.
Oh, yeah, good, yeah.
So there's a comic
Like
book.
whenever you're curious to actually understand
There's,
how
I think, also
that actually works,
classes of
you just ask AI. I think
So,
like,
yeah,
like books are kind of
there's
outdated
also
now.
Last year there was
So,
topic
guy
because
who
you
ran
read,
a,
the best way to learn now
there's
is
a lot that has
just
been done,
into
so
the
it's,
frontier.
like
this is speed,
And do like
these problems are in
It's a
speed,
self service
all
that
these
you
problems
be able
in
to
and see how it works.
Yeah.
Not
This
to a
is in
textbook
space,
in
this is
linear fashion, but where you want to
This is time.
understand how.
This is exponential space, this is exponential.
Oh, yeah. And that would be a really good follow-up. So,
it's on an island
March,
in Thailand.
Yeah.
And
we
we
had
flew
our
over,
talk
just talked about how we're
Sally
gonna use
and
AI to
physics
create this
and,
middle layer
yeah,
in
and
between
Silas.
the browser
I do.
and
Yeah.
the website.
Yeah. How do you meet
And that
people?
is going to be
How do
like
you meet people?
the
Yeah.
place where
Well,
we
it's pretty cool.
go
Um,
control.
and so that was,
What
you know,
kind of
obviously.
people?
Essentially, and have that be like an
I go to one every week. It's
between those
one is for
classes.
algorithms.
Yeah,
Okay.
these are just
Every week
papers.
just comes
Somehow
together
modify
and we solve
Yeah,
some
paper,
problems together.
paper.
Okay.
Yeah, that was how the group originally started.
Another one is like
before,
languages and
That's
stuff.
the
I
way
like
revived it
learning languages.
last year.
Natural human
Well,
languages.
the way I saw it is that there's a way
I want to learn more Indian languages as well, but I'm learning Vietnamese and
Oh, yeah,
Spanish at the moment as well.
There's also another one for
And I also teach people
I feel like I
Hindi.
just made that up.
So if you want to try it out, if you want to practice it, you said you were.
I like that. Everybody else in there.
So I think like that sort of stuff is best learned by like myself and team.
And we would go
Indicator that is
like, we also
some kind of
tried
yes.
to-
I mean yeah. Actually, the libraries here. They actually do have Hindi books. Yeah, so I was like reading. Yeah, I like audio. Probably audio too.
Right now,
Yes, or if you want to just have conversational.
So,
Are you
having every site.
not that
But there's always one that like
but the work you want to maybe like going to your apartment to like I know that a lot of like
Yeah, that's the company.
government related like services they use they deliver to you guys use the Hindi words. Oh yeah, they English because like most of the media for me like they just substitute words. Yeah, the average especially I think if you have a basic perspective, that will help. Yeah, I know. Yeah. If you want to learn like complex vocabulary and like the rules and stuff behind like in other languages as well, like how their sentence structure or like how their word structure works. Like Sandhi, for example, is like in Sanskrit and most languages you can literally take any two words.
I mean, that's how we solve the that's unlike so many
There's
things in our
rules
society.
for the sounds
That
and
we
stuff.
actually remember.
Like how
We remember how we made the first computer.
We don't know
based on
how
what
we
vowel
made it.
sounds, how you change it basically to join words together. If you want to learn that stuff, I would say try learning Sanskrit. Okay. Yeah, I'm not learning Sanskrit. It's very rules based actually. Yeah, interesting.
The parking thing.
The
Up
grammar.
there in front, parking.
Oh, sorry.
Yeah, parking tickets.
I thought you were taking it away.
Yeah, you could definitely get on the Zoom.
If anybody needs to validate parking.
So if you would do a PhD in math, what would you do?
So.
I don't have any.
Yeah, we got a whole margarita.
But I do think
Please take them.
I'll take a pizza up to Diogenes.
Yep.
So.
Take whatever you got left.
Caesar and I are going there right now.
I'll off to my next thing,
Yes,
everybody.
there's margarita.
Great seeing you all again.
That's good to see you. See you next month. Next month, I was originally planning to do lean, the theorem prover. Maybe we can still do that, but
Also cookies. So.
But we'll see, we'll see. I'm gonna be busy, so
Yeah.
maybe
Thank you for
we'll
the
do it.
Oh, do you know all the like I love lean memes of like just people with like syrup like the styrofoam
Yeah,
cups
like,
and
what do you
the
think?
drink in it.
Yeah, okay.
Like, oh, PhD stuff, yeah. I mean, it's something I wanna do.
I've not seen
I
those,
wanna
but
go
I'm
into
not
research field a bit
surprised,
more
yeah.
and see how it
And
is.
then,
If I like
I've
it,
seen,
if I
I
want
love
to or not.
complex stuff, so.
I don't really have any specific topics
But,
as of now. That would be-
Signal.
Maybe some broad fields,
I
maybe to actually go into the reading aspect.
Yeah.
I'm hearing that, like, for homework, like, all of the questions, yeah,
I think that's the only way that we can.
Yeah, well,
Yeah,
so
so I can't
Oh,
replace
yes.
a human.
So, yeah, well, no, but I just wanna
At the
say,
end of the day.
can you TM people on Zilla?
Oh,
okay.
I can,
Alright,
yeah,
yeah,
right
okay.
now,
So,
yes, but I'm thinking like,
there's,
like, obviously like I'm not gonna lose
so,
things like that.
I just
before
posted a
you
link
go.
to
Like,
the,
if it does, like,
Meetup Don't Be Evil conference.
I think like it
Oh,
would
okay.
be
So,
but,
and then, I wanna send you the link to the after party if
but
you're
still it is
interested.
possible.
Oh, nice. When is it?
So, it's, March 14th.
That it does.
Oh, I'm gonna be, that's when I'm gonna be at.
Oh.
I'm gonna be in,
Yeah.
Barcelona.
Oh, nice.
So
At the moment, yeah, I think that's
WASM
like,
guys.
yeah, I can't.
Talked me into going to WASM
Yeah, I
Radio.
can't
Since this,
produce creative
Danny
thought.
and Calvin and all
In
them,
those cases.
since this might be the
Yeah,
last
but don't
one.
predict on
So that's why I was like, okay. And
on
it
the-
also occurred to me,
Well,
something I
in terms
want
of
to do,
like
I'd like to
academic
write,
output, I think,
I'd like to
because
at least
it is
attempt a
still,
paper
like, quite a
this year
creative
if I can.
endeavor, right?
And the
Yeah,
paper that
that's
comes to
logical.
mind that I'm most
Yeah.
likely that I could actually pull off would be putting, putting a WASM,
Yeah, anyway, you have
runtime
both,
on
math
top
and
of
CS background, right?
SEL4,
So,
so that you have
the
a
auto-
super duper
intersection
secure
of those, yeah,
version of
is,
computing that's actually real.
machine learning.
I think that would be
No,
neat.
not quite.
And so
like
if
math
I was
for
able to
machine
pull it
learning
off,
is basically,
then I can make
like
proofs
developing
about the
new
compliant system
algorithms,
because
but,
WASM has
because, like,
formal
I
specs
said,
inside of Isabelle, inside
Sure,
of
I
Rock,
interrupted
oh
you.
yeah.
Yeah, so
And
like
part of the
math
reason why I'm
for
thinking
AI
about
is not
going,
like
why
it's
I
for
decided to
developing
go,
like new
was
algorithms
not only is
and
that
or like
relevant,
diffusion,
but it seems
for
like this
LLMs,
WASM
like,
IO was the only
the
conference
current
that had both
transformer
the
LLMs,
web
like you
side
don't
of
really
people, which I
math
do with my
program.
day job stuff.
So
But
not really,
all of the
but,
formal
for,
methods people who do WASM,
the
there's not many,
section of
but
math
there are
and
some,
CS
and I've met
is,
them.
is,
They're all gonna be in the
pure
same place at
proving,
the same
like,
time.
yeah,
Nice.
like
And this
formal
might be the
methods
last time
and
that
stuff, yeah.
happens, and so I'm like, okay, well, if
That's
that's
why I
the
was
case,
kind
then
of
I should.
enticed by it. I was like,
Is your
this
company
actually
project,
sounds
fighting
what I want. I want to do
Uh,
something on both of them.
kidding me?
And this is literally a game.
They're big,
Yeah.
no.
So we'd be
I'll
still
I'll
having
just,
issues with the.
well, I mean, yeah, but that's not.
So I would still suggest that,
I mean, I'm sure it
you
is,
should still,
like, that's not,
like,
that's not
get
the
into it,
most
but get into
material
it,
problem
like,
as far as
like,
I'm concerned.
like, mess with the foundations.
They didn't ask
You'll
me.
be stuck
They
there.
didn't ask me,
Yeah.
I don't know, I don't know how numbers work.
Yeah.
You see my
Which is
arithmetic.
lie, basically, yeah.
I don't know how numbers work, man.
So,
You want to share contact or anything?
There's other
Yes.
things, so in today's
You
lecture,
use the phone?
it just is
Yeah.
very easy to
Yeah.
jump into Lisp
Yeah, I don't
scheme.
have Instagram.
Yep.
It shows some
I've
Lisp
heard
Lisp
as well.
scheme programming and all.
Not a big deal. I mean, I use
Even
it
there
around.
are
use
big
it to, like,
applications
okay,
developing
uh,
Lisp scheme being used until today.
Yeah. Good to see it, yeah.
And another topic that it would be fun, quick, and help everyone is automata
How do I add
theory.
context? Oh, you just
Yeah,
call it
I've seen
and then
some
you-
talks on that, it's not an area that I'm super familiar with, but,
Yeah, so that is simpler than this.
Yeah.
Usually is the introduction, to graduate
Oh,
to
yeah.
logic, first you have to do
Yeah, that's it.
automata.
yeah,
But then
yeah.
I'll take it over.
And
Yeah.
the books are very there's a lot of good books.
You want more margarita?
And the plus side is that if you
Now
know
the
well
turbine
automata,
is run
they
as-
can, they
yeah,
can
R-A-U-N-A.
start with
Run as
rejects.
what?
Like,
R-A-U-N-A.
a lot of people go to
So
AI or like
C-H-A-
to
chat.
search for
A-T.
rejects patterns.
Yeah.
But you should just do
W-A-L.
rejects, and if you know
Oh,
well
Chatwala,
automata,
yeah.
there's
Chatwala?
different types of
Yeah,
automata.
Chatwala. No,
Yes.
Oh, yeah, yeah,
And
Punjab.
then you can do like
Yeah, you
state
think so?
machines,
Yeah.
and it's like,
Sounds good.
it's easier than logic,
Oh,
Yeah,
I
yeah.
use
but
that
it's
for Meetup.
also in a
Yeah,
talk.
yeah.
It's like more interactive.
Yeah, I have the Meetup.
Oh, yeah, for sure.
Because the
Like-
Yeah, I was seeing you were doing.
Yeah. Alright, we gotta get, GC's move.